this is Model 2. I changed the directions a little bit. This is actually going to run into tomorrow's lesson. So the derivative is ky, so I'm not giving you a specific on what k is, I'm just saying that it represents a constant. Find the general solution to the differential equation. So what also is missing from this is I didn't give you an initial condition. So we are not going to be able to figure out what that plus c is that we're eventually going to get within our step 2. But we will basically proceed the same way. We're going to separate the variables. And we will do so by cross multiplying, right? So we're going to get dy equals ky dx. I'm going to divide by y. I'm going to leave the k over with the dx side. So I have 1 over y dy equals k dx. And to reinforce, looks like the antiderivative is going to be a natural log, right? We have a degree of 0 in the numerator, and we have a degree of 1 in the denominator. So when we go to step number 2, right, we know that the antiderivative of 1 over y is going to be a natural log of the u value, which is the denominator. We're going to remember to put it in the absolute value symbol now, as opposed to just the parentheses, right? And again, reason why we're doing that is you can't take the natural log of a negative number, right? So the absolute value sort of reinforces that. And what we're going to do over here is we are just going to double check. If this is the original function and we find the derivative, the derivative would be 1 over y times the derivative of y. We're in terms of y, so we would say it's 1. So we are really good to go over here. There's no extra coefficient that we would have to multiply by. This is essentially the parent, function, if you like to think about it that way. And now we have to integrate k in terms of x. So k is a constant. So like if this was 4, we would do 4x, right? Or if this was 2, we would do 2x, right? So we're going to be doing kx plus c. Now, typically step 3 is to find the c value, but we're not, because we're just finding the general solution, which really means that no initial condition is being provided to you. So we will not be able to figure out what that c is. So we're going to go right to step 4, which would be to solve for y. So we're going to use our technique of exponentiating both sides. And we definitely want to use the base of e, since e and ln have that inverse connection that we really like. So once again, when we exponentiate both sides, our equation that we were working with now really becomes the exponents on both sides, right? We have that nice shortcut that we can see over here, e to the ln, inverse functions. So now we're left with the absolute value of y equals, and I'm going to also rewrite this like I did in the last problem. I can rewrite this as e to the kx times e to the unknown c value. And we can do that because when we multiply like bases, we add the exponents, right? So I just rewrote this a different way. And to solve absolute value equations, the solution we understand is positive or negative. So we have this. And further, I'm going to rewrite this another way. If you think about it, C represents an unknown constant, right? Could be 4, could be 1.2, could be pi, could be whatever, right? But it represents a number. And if you think about this, isn't this just a constant in and of itself, right? E to some number would just produce another number. So how this is rewritten is we just put a big C as the coefficient of e to the kx. And curious if this formula looks a little familiar. The letters are not necessarily the same, but do you recall the A-PERT formula that you learned in Algebra 2? Has the same exact formation, right? So this is our final answer here. We would not be able to figure out if it was positive or negative. Again, we don't know the C value. We don't know the initial condition. So step 5 is not to be done here.